Okay, recording is started.
Okay. Okay, so as I was saying right in the beginning, again, I'm just going to recap what I missed. Whenever you see a word which doesn't make sense to you, go to Oxford Dictionary, any other, just Google it or search it. But the key thing that you click on the right link, not any link. Make sure that it's a quality website you go into to get that information, and it comes with experience. So Oxford Dictionary or Wikipedia are very good quality sources in order to get the understanding of a certain word you want to understand. Okay, so we talk about integrated circuits, and as I was mentioning, I was just showing you that there is a passive low pass filter, high pass, passive high pass. Don't worry about what it means by the word passive, and this is a simple amplified circuit. But since we are talking, okay, so what I did here, any circuit does a functionality. So so what I write here is a circuit C1 with a functionality of F. So that's why I'm representing this as that this circuit is FC1, this circuit is FC2, and this circuit is FCN. So in an integrated circuit, in mathematical form, I haven't seen that written anywhere, but maybe I wrote it for the first time. You are basically integrating all the circuits from 1 to n in a chip. Either you can write like this, or you can use a summation symbol for the same. Okay, and that's what I showed you. That's how tiny that can be. That shows the scaling of the chip. Don't worry about the package's name or whatever it is. It's basically, it can look like this, and these are called SMDs because you can put these ICs on the surface. One of the ICs which I showed you here are through-hole ICs. You need some holes on the PCB in order to have the functionality of that particular IC. And I already went through that. One of the most important thing, what I can tell you right here in the digital logic gates is the NAND gate right here. You can design any logic circuit using only NAND gates. So remember that. So that's why if you have NAND ICs, you can do a lot. But nowadays, FPGAs are very popular. So better get comfortable using FPGAs and microcontrollers. Again, this slide is just to show you that the IC packages come in different forms and shapes and pins. You don't need to remember it. This is just because I'm considering all of you as have no clue about microcontrollers, ICs, packages. This is because seeing is believing. I'm just showing you that what ICs I showed you doesn't mean that these are the only ICs you can buy from the market, okay? So you can look into these ICs like this, okay? So this is why I'm showing you here. And that's the scaling. Just to show you, that's why at that time I was going to distribute you this, but anyhow, I have to replan on the fly. Okay, so we talk about it. Microcontrollers is basically, to understand microcontrollers, how it started, we need to understand the history of transistors. And the history of transistors is not complete. I don't know. Let's limit the history. We can limit it from vacuum tubes. Even before there's a lot of history. But things started with vacuum tubes, and the main feature of these vacuum tubes that it can amplify and rectify. But the problems given because of the heat and energy consumption and the size, you can see there, it led to the research to do something, doing the same in a tiny thing. And that's how, this is the first ever transistor built at AT&T Bell Labs. So what I'm trying to show you, it's a simply germanium material wire they used to make the first transistor. You don't need to have a lot of money. You need to be innovative to do something. The particle accelerator where I work at Cornell, it's a huge facility, or at CERN, I didn't work there, but it's multi-billion-dollar projects, okay? But it started with a small idea just like this. Like particle accelerators was a palm-top kind of a accelerator which researchers built at different research institutes. And because of the success of that prototyping, governments were able to invest on those project ideas. So anyhow, just to show you, this was one of the first transistors ever successfully demonstrated at Bell Labs, which led to the evolutionary process. You can see here vacuum tubes and different transistors, the legs, different packages, sizes, but eventually it came down to, so these are the symbols of transistors which you can see on the circuits. But what happens, now we have that power of ICs like we see on our laptops or computers, AMD resins, So all what we are doing is putting a lot of transistors which follows the Moore's law. Any question by now? Any question of anyone doesn't understand about IC packages? Why we came from vacuum tubes to transistors or anything like this? You can ask right now. Okay, cool. So now let's. So it took me 10 minutes just to go over that what we're talking about. So again, now you understand that microcontroller or microprocessor is nothing more than an IC package. This is one of the IC package, I'm just showing you here. SOIC, you can see. So these are the fundamental main blocks of a microprocessor. If you understand this, you can use any microprocessor. You can program any microprocessor for whatever needs you have. Okay, so these are the main blocks. So in the microcontroller, the key element is microprocessor. So understanding this is very important. This microprocessor is the brain of microcontroller, which can only understand prefixed set of instructions. So maybe I can ask all of you, how many English language words you can understand? Can someone tell me? You can say many, right? How many languages you can speak when you wanted to, right? But that's not the case here. Mostly between 30 and 50 instruction words it can understand. If you talk anything out of that set, it's not going to understand. Are you clear on that? So it has limited vocabulary. So you need to talk to this microprocessor in its language in order to have it do what you want to do. RAM or flash is ROM or flash is where we most of the time store programs. This is also memory for runtime usage, and I/O is for the input and output. Okay. So since it's a digital IC, it means all the pins is basically doing logic 0 and 1 in the voltage supply. So some of the important pins I can mention here. Most of the time, the power pin is located on is the last pin on the IC. Okay, so one thing here, you see this dot and the notch. This, on a package like this shows where the pin 1 is. Top left is pin 1. So you count like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be pin 18. So most of the time, the last pin is the power pin, and this pin is the ground pin. So I'm just going to tell you some of the important pins of the microcontroller. So as you can see here, I'm showing you the power, which can be VCC plus 5. So these are the symbols you use on the schematic you design, and these are the ground symbols you use on your schematics. So most of the microcontrollers coming nowadays, you can program designated pins as either be input pin or output pin. So let's say I program this pin to be an input pin. So it's only going to read is one direction. So it's only going to read whatever the logic is on that particular digital input. It can be an analog input, but over here I'm just mentioning digital. And this can be an output pin. Any questions on the packet side? Okay. Any microprocessor, microcontroller, DSP, or any intelligent brain on a chip or a package goes through this cycle. So remember, this is very simple, there's no complexity. So what it does, it basically fetches an instruction from the storage location, flash or ROM, whatever. It can be some cases it can be RAM. It decodes. Decode means it try to establish what I need to do. Because you write an instruction in one way, it translates it into machine language, and it's a big word, and it has to go through the decoding process in order to understand what he has to do, and then it executes it. So if you remember this cycle, it's a very powerful understanding. I'm telling you that. That's all what you do as an automation engineer, electrical engineer, electronic engineer, whenever it comes to a system design, which has a software element in it. Any questions? Cool. Yeah, so these are, for not you to understand, yeah, these are the sets what I was mentioning here. So you can see here, data transfer can have certain batch of instructions which microcontroller can understand, or microprocessor inside the microcontroller, arithmetic, logical, Boolean, program branching. So these are given as assembly language. By no means I have done this. Anyone has done assembly programming? Raise your hand. Yeah, 40 years. Anyone else? Cool. So I have done assembly programming. I have used instructions like this to program CPUs, microcontrollers, microprocessors. But even these instructions has to translate into zeros and ones. So what I'm trying to say is, so for example, this instruction will translate to, let's say, 001111. So microprocessor inside the microcontroller can only understand that language of zeros and ones. Okay? So I'm just showing you the power here, that what I'm showing you here is true for any microcontroller, DSP, microprocessor, and it's a sample set of Manmix. Okay, so let's now understand that how we can program a simple Hello World application for a microcontroller. So this example I did for Arduino. How many people know Arduino? How many people can program Arduino? I was looking at you because you say you know it, but you can't program it. So the reason of the popularity of Arduino is the simplicity. Okay, that's what it is. So let's understand this program. And this is more like a C program, C style, but so this setup thing only runs once. Okay, in this, you set up your environment or variables or whatever you want to set up when the program is running for the first time. So over here, what I'm doing, I'm setting the serial port. How many people understand the serial port? How many pins a serial port can have? Okay, 9 or 25. Okay, so these are the common ones, but nowadays we have USB to serial adapters, whatever the FTTH chips, we are not going to, yeah, so I'm just basically setting the serial port baud rate to 9600 bits per second. You are late, man. So this is the infinite loop, okay? So while loop is, this loop runs forever. Okay. So what it's doing, that it's going to print hello world to the serial port. Okay, that's what it is. I'm writing to the serial port hello world. It's going to wait 1000. How many? Milliseconds. Cool. So that means how many seconds? 1. So that's exactly what it's going to wait for 1 second, and then it's going to print again, 1 second wait. So that's a simple program. Any questions on that? So okay, so another advice. If you don't understand something, don't just simply sit. That's exactly like getting scared of the finals. You understand? You're afraid of the finals because you're not taking the right actions at the right moment of time. To make your life easy, always, if you do not understand even a single thing, you ask me a question, if I don't know, the only thing what I'm going to say is, give me time, let me research or read about it, and I'll let you know. Okay? So, again, trying to help students have a successful journey. Yeah, so what happens that this program, because we have written in English, because we are comfortable, we can read it, we can write in it. Now this program gets fed into a compiler or an interpreter, right? If I'm talking in, how many people understand French? So if I'm talking in French, you will understand. So what's going to happen? So he's going to help us, right? So if I'm talking French, you can translate in English, right? Yeah. So that's what we do, right? That's exactly what happens in the computer world. You're writing a program which the chip doesn't understand. So you put the interpreter there. We also call it as compiler. Without going into the complexity, it's nothing more than just an interpreter. So it's going to convert your instructions into a which language? Which we call it as machine language. Cool. Good. And it's a place which we are going to store it in a memory location, any name you can give, RAM, ROM, flash, doesn't matter, on the SD card. And the microprocessor, DSP, the micro, whatever it is going to fetch that instruction and go through which cycle? So once the instruction is taken by the microprocessor, what it will do? I just told in the last slide. It's going to decode it and it's going to execute it. And that's exactly what's happening here, right? So you see the hello world as an output. This is a terminal program, a small terminal program on the PC. And you see the hello world every 1 second. So see, this is a program. We got ourselves introduced to ICs, the packages, how we program it, and this is one of the simplest programs, the hello world. So what I'm trying to emphasize, these beginning lectures, myself or anyone else you came across, any course what I'm advising, if you're not clear about the basics, so basics is just like foundation of any building. So if a building doesn't have a good foundation, what will happen? That's how simple the life is. So you need to have the basics right and strong. And don't run after money. Run after quality aspects of your life. And maybe it's away from the lecture. So anyhow, this is the Arduino, and this is like again another application to blink an LED. Okay. So what I'm doing here is just trying to show another applications. We did Hello World, and here is in the digital domain or electrical electronics. It's kind of a Hello World blinking application is like a Hello World kind of an application. Okay, so I'm not showing you. I'm assuming that the +5 is connected, the ground is connected to the supply, and this resistor is what you call it as a current limiting resistor. It limits the amount of current going to protect the LED, and that program when we will run, we just have to, I'm going to show you what kind of a program I'm going to run. So this is kind of the breadboarding. Anyone who does not understand a breadboard, raise your hand. So all familiar, right? So what I did is just simply took the 13, connected here, there is a resistor, like mostly a 100 ohm resistor, connected with the LED. So see here, can someone tell me whether it's the positive side or negative side connected? Okay, why?
Because the negative side doesn't have the ground.
No, but how you?
Oh, it's the notch in the lead.
Did you understand what he said? This notch, because when you hold the LED from the whatever the pins you have, the longer pin is anode, okay. But once you cut it and you put it into the board, how you recognize that which side is? So this notch tells you that which side is on the anode and which side is cathode. Anode is plus or negative?
Negative.
Who said that? Cool! Awesome! But, the most important thing I like about it, you said what you thought is right. Even though it's wrong, it doesn't matter.
You might get that a lot.
Doesn't matter. Doesn't matter, man. The thing is, whoever doesn't matter. My job in whatever I do, wherever I do, is to inspire individuals. Okay, if you get inspired, I won. I win most of the time. So anyhow, how we do it? So we had the prototype circuit build. So I'm going to. This is the ID, how the Arduino ID, whoever has already experience look like. I'm going to run it from my whatever machine I'm using. And here's the program I written here. Again, setup only runs once. So I'm setting pin 13, the mode as an output. Okay. And this is an infinite loop. I'm going to make the output as high. I'm going to wait for how many seconds?
1 second.
And I'm going to write low. Again 1 second. So that's how it's just like a heart, right? Any questions here? Okay, so this is the powerful microcontrollers I'm going to show you here. So a powerful, okay. What about a powerful truck? What is it? Let me ask you that.
V8.
Yeah, what makes it powerful? Horsepowers, more features, more functionalities, right? And that's nothing more, that's exactly what we do in a powerful microcontroller. So we collect a lot of smaller IC packages and we try to fit into one small tiny IC package, okay? So I'm just trying to show you here that in the microcontroller what we do, a chip which can be a program memory separate coming, a RAM or a microprocessor or an AD's analog to digital converter, an oscillator, or whatever functionality of ICs, we can find it separately. We try to combine it together as one package. We call it as IC is one thing, but here in this microcontroller. Any questions you have now? Okay, so again, I'm just going to show you some of the block diagrams of powerful microcontrollers without going into the details. Seeing is believing. And this block diagram is for a microcontroller for space applications. Why I have this up there is just to complete the discussion that IC doesn't mean that you can use any IC for any type of application. No. There are IC made for military purposes. There are military grade ICs. There are ICs which are made for space applications. Those are radiation hardened ICs. So simple as that, more expensive ICs. The military ICs are kind of maybe 10 times the cost of a normal, regular general purpose IC. And the space grade is time maybe 100, sometimes maybe 1000. I don't know. So, does it make sense? So that's why I'm just trying to show you here. Okay, So again, relating to applications, since anyone have any question on microcontrollers that they don't understand what a microcontroller, how it looks like, how to program it, as a general overview, if someone has any question, you can ask me right now, because now I'm going to move on to more kind of application side, examples and applications. Okay, no questions. Cool. Okay, so what you see here is a smart card. All the text you see here has microcontroller application in it. So do you want me to go through all those applications, how they are done? It doesn't make sense, right? To be as a smart teachers, what I learned from that, to make it simple. So that's how any system, physical, electrical, virtual, whatever, these are the three main aspects of it. It has one input or multiple inputs. It has some processing element in it, and it has an output. For example, how the car goes, how the car runs. What is the input of the car?
Gas.
Or
Electricity.
input, what is the output?
Moving.
See, and what is the processing element?
The engine or the.
See? So see, that's how simple it is for you to, okay, what is your input, by the way? As a human being, biological organism, what is your input?
Food.
Okay, what is your output?
Whatever I'm feeling like, I guess.
And what is your processing element?
Hopefully it's my brain.
Very well said. So, long story short, so life is simple, life is very easy to understand, and please do take it seriously. If you do not understand any word, anything what you see, you hear, verify it. This will make your life very easy. Smart students are whatever. I'm not a smart student, but that's exactly what their habit is. They just break it down into very small, manageable pieces. The important element in this diagram is this thing. So this, remember this, whatever you do, master's, PhD, in your academics, this line looks simple, but that completes what I'm trying to show you here. So now you can understand any application, mechanical, electrical, electronics, space, and you just think what is the input, how we are processing it, what is the output, and how we are correcting ourselves. Okay? This feedback mechanism, AI, ML, DL, machines, they do it very good because of the processing power they carry around. Okay, so this is a real application now. So this is a simple fluid level or I'll say a water level sensor. So it's a fluid level sensor using Arduino. This is just for the display, what information we want to display. As you can see on the top right hand side, okay, I'm using an Arduino. And very simple. So these are aluminum wires, as you can see here. The sensor assembly consists of 4 aluminum wires, and based on where the fluid level touches, you will get the respective analog input as a signal. Okay. If there is water, you will get a different strength. If there is no water, you will obviously determine both in these two cases. So these are analog ports. Analog to digital converter is connected here. So this is to turn on the transistor, to run the motor, to fill the tanks. Okay, I'm not showing the piping, that's not my job, that's mechanical, whoever it is. So it will fill the tanks, and this is for the buzzer for any level, whatever functionality you want the buzzer to be on. If you want buzzer to be on, okay, the water level is too low, turn it on there, or if you want the buzzer level to be here, it will turn on, or both in this case, okay? So, I don't know what else I should tell you here. So there is nothing more than 4 analog inputs, which plus the fifth one, you're monitoring in the software program, and you're turning the motor on whenever you want the motor to turn on, or you're turning on the buzzer by sending one signal here or one here. Okay, because once you send a signal 1 here, it will turn on the transistor which will enable the motor and run the motor to do the respective job. Exactly, it will do it here. Any questions? Someone has ever used a 16 by 2? Yeah.
So is it inputting the 5 volts through the water, and then as the water touches those aluminum, it's reading that 5-volt impulse?
Okay. Very good question. Okay. First of all, I took it from the web. If I'm designing it, I will never design a thing like this. Okay? But second most important thing, there's always multiple ways to do the same thing. Do you understand that? There are always multiple ways to do the same thing. So I would have done in a totally different way where there is only a passive element in there, which maybe has some battery element in it, and it goes with it. But this guy, so that's a very, I was expecting a question like this from someone in the audience. I will never put a direct 5 volt into the tank. Either way. Okay? Cool. Anyone use 16 by 2 LCDs? I think most of the time they are very rigid, but these are the commercial scales. So what I showed you is the kind of a prototype how you do it, but something in the plate has to look good for someone to buy it. So the package is pretty good. Make it rigid and RO2. And depending on what kind of a circuitry what they are using it, I don't know, but I'm just trying to show you that's how the fluid level sensors look like in the industry. So these are the which is for space applications. The reason of showing you this, there are only limited companies who does work relating to manufacturing microcontrollers or ICs for space applications. These are some of the, so it's important for whoever is learning on microcontrollers to stick with those companies and learn their tools, how they do it, learn their chipsets, so that you can cover the broader industrial segment space. Make sense? Okay, so for example, if I'm teaching you this course, I will not stick you with one board, one micro, or never let any instructor do that to you. The only thing, if someone asks you, do you know microcontrollers? Which microcontrollers you like? Your answer should be, give me any microcontroller, any microprocessor, any DSP. Because you know the cycle, the input, the processing element, the output. You can learn the new tools. The entire advancement in technology is to do just one thing, is to make humans' life easy, not difficult. Okay? Hopefully that makes sense. Okay, so course objectives is getting comfortable in using any microcontroller. Again, it's bolded for any potential applications. And when you program chips like the term they use is embedded firmware developer for industrial or consumer applications, become a better digital circuitry system designer, because you cannot be a simple embedded programmer without understanding digital logic, analog, circuitry, connections, prototyping, overall system architecture. So you are stepping yourself into a road of learning and practicing something rigorously. So that's what I just wanted to show you. So I have some applications relating to microcontrollers. I already have the videos up and running, and I'm going to show you one by one. So see, these are DoorDash delivery. So they are using drones or anything like this. You cannot imagine that they are not using a microcontroller. Okay, so you can see here they are just flying with intelligent coordinates going from point A to point B and delivering the package what they need to deliver. So since I'm lacking time, so I'm going to skip that and go to the next one. I want to show you something. Here you go. That's a cool one. So what's that? You guys know that, right?
Are those the drones with the LEDs that like do the sky shows?
So these are drones with LEDs, and they're synced. They're AI driven. They're launched. I think that's a cool demonstration of what a software can do, what microcontrollers can do, what the integrated world of mechanical, electrical, electronics, and digital can do. Okay, so that's one thing, and let me show you this. Okay, this is the term. Here you go. How many people know about this company called Boston Dynamics? So let's see this guy. So he's forgot his tools. So he's going to send an instruction to a humanoid. Here you go, and see what he's going to do. You cannot imagine a system like this not using a DSP, FPGA, microcontroller. Yeah, so what I'm trying to get into endless applications. Okay, so he forgot that, so he ordered it with instructions in the package, and see what he's going to do. Yeah, we can talk about getting terrified, but I'm not. So he just needed his.
You guys think of the Costco project,
Cool. Yeah, I like it.
I don't think we have the budget for that. That hardware to build it, everyone's kind of jumping around like that.
360s there. We just put it in the notes.
So, I think with the end of this video, my time is kind of 45 minutes up. Anyway, yeah, please.
So with something like that, or something like the smart card, can you do that all with one microprocessor and just one long code, or do you use multiple?
If the scale of that thing is small enough, with the limited features, the answer to that is most likely yes. But I cannot say yes, no. So, again, everything starts small. They gone that big without doing a lot of experimentation, prototyping. I think it must have taken them maybe 5 to 10 years to come to this. But that's a very good example of an AI. Okay, so any other questions? Anyone? Thank you very much, man. Okay, one thing I'm going to show you. As mentioned by Dr. Adil, I published a book, my first ever, Life Impacting Reality Stories. Dr. Adil can distribute it, but I wanted to show you the best teacher of my life. The best teacher of my life, he gifted to me this book. This gift is the sweetest gift I could have ever received. And that's on quantum mechanics. He thought that I was his good student, very humble enough. But anyhow, I'm just trying to, if anyone interested in knowing him, just go to here's his picture here. So I like to show him, not advertise myself, but the quality teachers because of which inspirations I am here. Okay, cool.
Thank you very much.
Really appreciate it.
Any questions, any comments? Any joke?
Who is interested interested in AI, by the way? Why you are interested in AI?
I like building things and taking things apart.
Cool. So why you like AI?
We're trying to use it for our capstone project.
Doing what?
We're trying to make a drone that follows you around.
Like the one which,
Yeah.
okay.
And stays at shoulder height and.
So you're using TensorFlow or something like that?
We have no clue what to use.
Okay, who else is there?
For a second, we have.
I know, I tried. Doesn't always work. So.
The thing is, okay, maybe I can, again, I think I showed right in the beginning, I told you guys right in the beginning, you think that you are on the difficult track, you're difficult project, but believe me, if you plan it right, if you break it apart in manageable pieces, things get very easy and simple. Okay, practical example, one of the organizations, my first organization I was working, it was a kind of a semi-military organization, so they had to take a tank up on the mountain. So the soldiers or the captains or they said we don't have the capability to lift a tank and take it all the way up onto the mountain. So the head of the organization, very well-known individual, without mentioning his name, so he mentioned, okay, how you when in a conversation with the colonels or whatever the majors, he said, how you build it? They said that we took that part from there, that part from there. So he said, he won't tell you the solution, just break it down and take all the pieces. And that's exactly what they did. So they carried the pieces up on the mountain and they collected over there. Okay? So yeah, things are difficult, but if you plan it right, if you plan it wrong, bad luck. You have to plan it wrong, right, and take the careful measures to make sure you don't fail.
And the first few times you're gonna get it wrong. Then you try again and again until you get it right.
Right, yeah, so being wrong is be very open, yeah, I was wrong, that's fine. You fail, I'm okay, I fail, I didn't put enough efforts. Fear is your biggest enemy. Never let it nurture in your heads or in your hearts. In any aspect of your life. If you really need to enjoy the gift of life, which I think I did, I care the least about that thing, the fear. Okay, cool, good, nice to have you. Yeah.
Would you say fear's your friend then though, because it encourages you to keep doing stuff and not be so fearful?
Sorry, can you repeat that?
Would you say fear's somewhat your friend though, because then it helps encourage you to go attack those things?
Okay, so again, you're getting into management side. So, no, I think, in my opinion, the word inspiration is the key aspect, and that's the ultimate winner. Fear is not. Because what history has proven, if you fear someone in a, big enough, it breaks. If you put enough load or too much load on something, it breaks. So it's up to you what you like to see. You like to see things grow up or break. So that's how I see things. Simple as that. Any other questions? Your difficult questions, sir. So why not let's have a decent, honest opinion about the presentation without being clapping. How do you feel about it? Did you learn something? Or I was just joking or just kind of a piece of whatever?
I feel like I brought a notebook.
Same here.
Cool. So see, that's why the recording is done. And you can put the recording and please share with everyone.
Yeah, I'll let Mike Newtown do that. Yep.
This is called planning. So it's not for me. So if someone is fearful of me seeing presentation, it means he or she or whatever, they have fear. I am whatever I am, and I try to be corrected as I go along. I'm nothing more than a student. Believe me, I told all the faculties, I will always be one. Okay? So I have this, I normally don't wear this, but I have this just to look good. And my wife insisted, you have to wear this.
Thank you for
It was
everybody.
fun.